This video is basically a direct continuation of our previous video. So we've learned about the process of optimization and the kind of algorithm or basic steps to take to approach optimization problems. And in this video, we are just looking at additional examples of optimization problems. So if you're not quite sure how to do these things, take a look at the previous video lecture and review and remind yourself, and then we'll dive right into examples in this video. So let's take a look at example 1. At a local lake, a lifeguard has 500 meters of buoyant rope to mark the boundary lines of a rectangular swimming area. She does not need a boundary line along the inside of the swimming area where there is the beach. What are the dimensions of the largest swimming area that this lifeguard can make? So let's just kind of dig into any details, any words in the question we might not be sure of, and then we'll make our diagram. Buoyant means that something floats. So basically we have a rope that's going to be floating in the water and marking out boundaries. We'll make our diagram over here. We can add some color coding. So we're going to have our beach. So this is the sand on our beach. And then we're going to have our water. And we are going to have a rope going out into the water. So the rope is going to go out, and that forms our rectangle. What else do we note from the question? We know that we have 500 meters of rope. That's like going to be the perimeter of our shape. And we want to find the largest swimming area, and we want dimensions. So in our final answer, we're going to be listing the dimensions. We're trying to maximize swimming area. And so let's actually go through our steps here and mark things off as we do this. So draw a picture, determine your goal, find constraints, solve for single variable, use calculus to find the extreme values. So we have drawn a picture. We have determined our goal, and our goal is to find maximum area. Max area, and it's max area of a rectangle. Find constraints. We know that all our values need to be positive. I can't have a 0 or a negative width or length or area. And let's add an extra little sketch up here and think about what we know about rectangles. So I'm going to be talking about the area of a rectangle. So area is going to be length times width. I also know something about the perimeter. So I know generally with a rectangle, I'm going to have perimeter is going to be 2 times the length plus 2 times the width. But in this case, remember my rope only goes on 3 sides. 1, 2, 3. So I don't need this length here. I'm not using rope along that portion, which means my perimeter here is going to be 2 times the width plus 1 times the length. And we know that we have 500 meters of rope, so I know that that's going to be equal to 500. And remember, one of the points of doing this is that we want to be able to define everything in terms of a single variable. And so basically we have area equals length times width. And I have perimeter equals 2 width plus length. And we're going to define everything in terms of width. So let's rearrange our equation here. Length equals perimeter minus 2w. Length equals 500 minus 2w. And now I can use substitution and put that into my other equation here. And so area, I'm going to move this off to the side here. Area is going to be length, but instead of length, I'm substituting in how we've defined length in terms of the width, 500 minus 2w, and width is just w. And let's label that on our diagram here as well. So I'm going to have width, and the length is 500 minus 2 times the width. And we'll just add a couple extra labels in here to be clear. This is our swimming area. and this is our beach. And let's define a variable as well. Let W be width of swimming area. So we're finding and so we've defined everything in terms of a single variable now. So we are finding and optimizing area as a function of width. So let's write out our equation once again, and then we're going to optimize. We're going to do so by finding the derivative and setting it equal to 0. So let's start with that. So area as a function of width is equal to width times 500 minus 2w, and it's easier for us to factor when we're not in, or it's easier for us to derive when we're not in factored form. So we're going to expand and multiply these two together. So area as a function of width is equal to negative 2w squared plus 500w. And let's think about any other constraints we have. Let's go back to that for a moment and think about what are the maximum and minimum possible widths. So one thing we could do, we can imagine that we have our beach. I draw two quick examples here. So we have two extreme cases to consider. In one, our width is set equal to 0 and the rope is just stretched right along the beach. And so that's the minimum possible value for our width. So our width can be as low as 0, well, I guess it can physically. We don't have an area at that point, so it has to be slightly greater than 0. But mathematically, our width is greater than or equal to 0. And alternatively, I can have the rope going straight out and straight back in. So rope goes out, folds back over itself and comes back in. And I'll actually show a little bit of width here, but technically there is, technically our length here is 0. So in this case, 250 out, 250 in. So our width is less than or equal to 250. So together, this gives us the constraint that our width is between 0 and 250. So we'll keep that constraint in mind as we work. All right, let's find the derivative and set it equal to 0. So I'm going to switch my color here, and we're going to set our derivative equal to 0. And we're doing that to find the critical point. So we know our endpoints that we're going to test. And we know that they aren't going to be our correct value because, I mean, the area of this shape is 0. The area of this shape is 0. That's obviously not maximizing our area. So we're going to need our critical point. So let's find it. So my derivative is going to be a prime w equals negative 4w plus 500. Set it equal to 0. 0 equals negative 4w plus 500. 4w equals 500. W equals 125. So this is our possible max. Remember though, we need to confirm if this is a maximum or a minimum. And in order to do that, we are going to compare values on either side of that value and make sure that our graph is switching from increasing to decreasing. So we'll do our little table and let's check our interval. And I'm going to be looking at my interval from 0 to 125 at 125, and our interval from 125 to 250. So just a quick reminder, where are these numbers coming from? These are our endpoints, and my possible max value here is my other point. After we have our intervals, remember we choose a test point within each one. So we're going to choose a test value between 0 and 125. And I'm just going to choose 1 and 125. And let's do 200. I'm going to plug them into my derivative. And that's going to tell us something about the slope of our original graph. And once again, remember, we don't care about the actual value of the number we're going to find here. All we care about is the sign. So we are going to take the derivative function, negative 4w plus 500. And we are going to evaluate that function for our first test value of 1, and we get a positive number. So positive, which means my graph is going up, positive slope. At 125, we already know it equals 0, but we can still plug it back in for a quick sanity check. Yes, it equals 0, which means my graph is neither increasing nor, actually, 0. So my graph is neither increasing nor decreasing at that point. And evaluating the function for 200, we get a negative value, which means my graph is decreasing. So therefore, this is a max. All right, that's great. So we have successfully found our endpoints. We have successfully found our critical point. We have successfully confirmed that our critical point is a maximum because we set our derivative equal to 0, and we tested points on either side and determined that it does follow the correct pattern for being a maximum. Now let's actually interpret our results. So the question, we've shown that the possible max width, or the max width, is 125, but we haven't actually stated the dimensions which is required to answer the question. So let's finish this up. Therefore, so our width is 125. Our length is 500 minus 2 times 125. Remember, we're just using our equation from up here. 500 minus 2 times 125 is 250. Therefore, dimensions of large, I'm going to rephrase that. Dimensions that give largest area are 125 meters by 250 meters. And there we go. That's the entire question. I'll zoom out so we can look at the whole thing all together. And let's check off that we used calculus to find our extreme values and then answered the question. Looks pretty good. I will just remind you as we go that it is a good idea for you to pause and attempt these questions on your own before watching me do it. So, because if you just watch somebody else answer the question, then you can be like, yeah, I get it. That made sense. But then when it comes time to do a question on your own, you suddenly realize, oh, I'm not actually sure why he did this part, or how did he know how to find that? So make sure you're taking the time to try to test your own knowledge and build your own understanding as well as we go. For our second example, that we actually already have a video working through how to solve this, so I'm not going to work through this together in my video here. Instead, I'll just provide the link either in Brightspace or in the video description for you to go to the Waterloo website and watch the video on the CEMC website. Moving along, one of the other applications for optimization, one of the other types of optimization problems we work on are related to economics. So let's talk briefly about optimization in economics, and then let's dive in and do some practice work with that. So first of all, definitions in economics. There are 3 terms, 3 symbols, and 3 types of main functions we will deal with in this course when we talk about optimization in economics. First is cost. We use C of X to represent that, and this is the amount of money spent to produce X units of some product. We have revenue. R of X, and this is the amount of money collected from selling X number of units. And we have profit, P of X. And this is the difference between cost and revenue to produce and sell units. So basically, how much money did we earn as a net profit? So we just had to spend money, that was our cost, in order to actually build our units. And then revenue is the money that we brought in. Economists use the term marginal to indicate the rate of change in cost, revenue, or profit with respect to the number of units produced. So we're finding marginal cost, marginal revenue, marginal profit here because it's all based on the number of units sold. For instance, marginal cost refers to the rate of change with respect to X in cost to produce X units. Ultimately, a company is most interested in its marginal profit, which tells them the per unit net income of the company after producing and selling X units. So how much money are we making per unit? And so notice our keyword here when we're talking about marginal, it's a rate of change. Rate of change is one of our telltale calculus words. And so what that is telling us to do is that we're going to need to take the derivative. Good thing we learned how to do that already. Take the derivative. And so when I see marginal cost, we're going to be finding C prime X. If we're going to be finding marginal profit, we're going to be finding P prime X. And if we were finding marginal revenue, it would be R prime X. Since profit is the difference between cost and revenue, it relies heavily on the number of units sold, which is directly related to the price charged per unit. A consumer's decision to purchase an item and the quantity that they are willing to buy is largely influenced by the sale price. A lower price per unit will result in many people purchasing units. However, if the price increases, fewer units will be sold. And we can kind of sketch that really quickly. So we can think about number sold versus price. And so price is our independent variable that we can change. Number sold is there. And so if the price is really low, our number sold is going to be really high. And as we increase our price, less and less people are going to want to buy it. We can also think about our profit as a function of price. Actually, yeah, profit or... Yeah, we'll go with profit. At the extreme, if the price is $0, how much profit are we making? Well, 0. I had to... Actually, I'll go with revenue. So how much money are we making if the price is 0? Nothing. I'm gonna sell, I'm gonna give away a whole bunch of units, but I'm not gonna make any money. And what if we set the price really high? So each ice cream cone costs $3,000. Maybe somebody's gonna buy it, but generally nobody's gonna pay that amount of money. And so we have our two extremes where we're gonna make no money, and in between, we're gonna have some kind of, often a quadratic function, where there's that sweet spot in the middle where we maximize, we find the price that allows us to maximize our revenue. The demand function, little p of x, so the demand function is the price per unit that a company should charge in order to sell X number of units. So demand function is going to give us the price. And this is little p of x, which is a little confusing. Thus, the revenue function is the product of the demand function and the number of units sold. So our formula for revenue is p of x times x. So basically, we have our three main aspects here: cost, revenue, and profit. And in order to find the revenue, we take our price per unit times our number of units. So revenue equals price per unit times our number of units. once again, just to label it clearly. So revenue is our money in. Revenue is price of 1 unit, so price per unit or unit price times number of units sold. All right, now that we have some idea about the terms and the formulas involved, let's go ahead and try answering some questions. Oh, I did not intentionally choose ice cream as my example a moment ago, but our first example involves ice cream desserts. Let's read the question and let's do some calculations. A fast food restaurant chain wishes to market and produce an ice cream dessert for the launch of the next blockbuster movie release. The owner of the fast food chain hires a mathematician to produce the demand and cost functions for this ice cream dessert. Based on market trials and the projected monthly sales of X ice cream desserts, the demand function is found to be P of X equals 30,000 minus X over 15,000. Remember, demand function is giving us our price. So that little P there is for price. The total cost in dollars of producing X number of ice cream desserts is C of X equals 3,500 plus 0.76X. And this is just a linear relation like you've seen since grade 9. And so we have like our initial amount. So it's going to cost you like $3,500 in supplies or whatever. And then an additional 76 cents per ice cream dessert. Remember, when you see the word marginal, we're being asked for the rate of change, which means the derivative. And so example 1, part A, determine the marginal revenue for monthly sales of 5,000 ice cream desserts. So we're having marginal, that means it's going to be a derivative. We're having revenue, so it's going to be R prime X. And monthly sales of 5,000 ice cream desserts, that is going to be our X value. So first of all, let's start with our revenue function. R of X is equal to P of X times X. So price per unit times units sold. And let's plug those chunks in. So P of X, remember the price per unit sold is given by its own function up here, the demand function. So let's sub that value into our equation. So instead of P of X, I'm going to write 30,000 minus X over 15,000 times X. And we actually know our X value, but for now, we're just going to leave it as a variable. And can we tidy this up a bit? Yes, let's multiply through. And so we're going to get, I can split this into 2 chunks. So I'm going to have 30,000 divided by 15,000, which is a 2 times X, so 2X, minus X times X is X squared over 15,000. And I think we're good there. We can write it another way just to help us visualize as we find the derivative. 2X minus 1 over 15,000 X squared, because now we can think of it as a constant multiple question. So R of X. So I stated my original function. Now I need to find the marginal revenue. Remember, that means I'm going to need to find the derivative. So let's find the derivative, and I'll switch colors here. R prime X is going to be 2 minus 1 over 15,000 times 2. So I'll make that into a 2 times X. Can we simplify that a little bit? Yes, we can. R prime of X equals 2 minus X over 7,500. All right, and we know our X value that we're going to evaluate for. So let's plug that into our function now. R prime of 5,000. So what is the rate of change of our function at 5,000? What is the marginal revenue? What is our change in revenue at 5,000 ice cream desserts sold in the month? And that's going to be 2 minus 5,000 over 7,500, which is going to be approximately equal to 2 minus 5,000 divided by 7,500 1.3 repeating. And we're dealing with money, so we round to the nearest hundredth. So therefore, marginal revenue. Remember, it's a word problem. We should write out their concluding statement and make sure we've actually answered the question being asked. So therefore, the marginal revenue is $1.33 per ice cream dessert. And remember, it's a rate. So when I'm finding marginal revenue, it's a rate of change. And so it has to be something over something. So our unit is something over something. And in this case, it is dollars per, I'm just going to say item to describe it in general terms. But in this case, it's dollars per ice cream dessert. And actually, we should add another piece of information that we're saying that this happens when the sales are 5,000 per month. So I'm just going to add that information in because I forgot. So therefore, marginal revenue is $1.33 per ice cream dessert when 5,000 are sold per month. All right, that was part A. Let's take a look at part B. What does this really mean? As we already answered up here. For part B, we are asked to determine the profit function. So recall that profit is equal to revenue minus cost. So basically profit equals money in minus money out. And so it is possible to have a negative profit. That just means that we're losing money. And we have our R of X function. We have our revenue function that we found in the previous question. So this is just being carried on down to here. And our cost function was given in the original part of the question as well. So that's where these values are coming from here. That's where these formulas or equations are coming from. All right, let's plug in what we know. So I want to find the profit. I know the revenue function, so let's plug that into our equation. We'll substitute it in. 1 over 15,000 times x squared minus 3,500 plus 0.76x. And let's try to bring this together and see if we can collect like terms or do anything with this. Let's be careful. There's actually a small mistake here. Notice our revenue has an x in it, and the x is missing from here. So let's put that back into our question right away before we forget it and make a mistake. All right, let's tidy this up a little bit. So we're going to have 2x minus 1 over 15,000 x squared minus 3,500 minus 0.76x. Please be careful with the distributive property. I still see people making mistakes like this. We can think of this, we can rewrite it as plus -1 times 3,500 plus 0.76x, and I'm distributing that -1 to both terms inside the brackets, and that's why they are both now negative. So please watch out for that. It's an easy mistake. I see students make that mistake in grade 9 and in grade 10 and 11 and 12. It's a really common mistake. So just think twice and double check when you do that work. All right, we got everything together. Do we have any like terms? Yes, I have 2 terms with an x variable. So let's collect them and let's find out what our profit function is going to be. So P of x is going to be equal to -1 over 15,000 x squared, so highest degree comes first, plus 1.24x minus 3,500. And all the question asked us to do here was find the profit function, so we're done. And what if I wanted to find how the profit changes per item sold? Then I would find the marginal profit. So this is just kind of an aside. Marginal profit. And that would be my change in profit per item sold. I highlighted that because that tells us it's a rate. It's one of our telltale calculus words. And that means that if I wanted to find the marginal profit, I would find the derivative. I would find P prime X. And we're going to need that as we head into part C. Part C asks us to determine the marginal profit for monthly sales of 5,000 ice cream desserts. So I already have my profit function here that I found in the previous question. I've just carried it down with us. Let's find the derivative of that function. So remember, marginal profit, marginal means change in. We're going to find the derivative. So P prime X, and I'm actually going to switch colors here. P prime X is going to be equal to -2 over 15,000 x squared plus 1.24, or P prime X equals -x squared over 7,500 plus 1.24. And we know we're evaluating when X is equal to 5,000 units sold. So the change in profit or marginal profit at 5,000 units sold is equal to -5,000 squared over 7,500 plus 1.24. And I do have the answer key in front of me, but I like to actually do the calculations and double check as I work. So we're going to have 5,000 squared divided by -7,500 plus oh, I made a mistake. I forgot to bring my 2 down. Once again, I'm going to leave this in because I want you to see that teachers make mistakes too. But I immediately noticed that my numbers are way too big. So I go back for a quick sanity check, and the mistake's right there in front of us. So not too hard to see. So yeah, right here from the start, this 2 is gone. All right, let's try this again. So -5,000 over 7,500 is -2/3 plus 1.24. Therefore, our change in profit per item sold at this point, P prime of 5,000, is approximately equal to 0.57 per dessert. And it's positive, so that means that per item sold at this point, we are earning 57 cents. So what does this really mean? Well, let's interpret and write our concluding statement. Therefore, with sales of 5,000 ice cream desserts, the company's profit, and it's positive, it's a positive rate of change, so it's an increase. Remember, it is possible to decrease. They can lose money at a certain point. So with sales of 5,000 desserts, the company's profit increases by approximately 57 cents per dessert sold. And once again, watch your units. Make sure it's per. Don't just tell me dollars. It has to be dollars per unit because we're finding marginal profit. Marginal profit means change in profit. Change means it's a rate. It's something per something else.